So what holds two molecules together? Intermolecular forces is what we're going to look at right now. If you want to run this simulator, you're welcome to it at the URL there. Alright, so first of all, we're going to look at the difference between a solid, a liquid, and a gas. A solid, all of the particles in a solid are held together quite strongly. Basically, there's not enough energy present in the system to overcome the attractive forces between them. When changing from a solid to a liquid, the system's gained enough energy, we see this as an increase in temperature, so that the molecules are basically able to spin. They have a little bit more rotation. They have rotational freedom. Okay, when we switch to a gas, however, this means all the attractive forces between particles have been broken. Alright, the system now has enough energy that they've overcome any attraction that the particles had to one another. Right? The stronger the intermolecular force, the higher the melting and the boiling points is the take-home message for what we're going to look at. The first type of intermolecular force is known as London or dispersion forces. Okay, they can also sometimes be referred to as van der Waals forces. They're the dominant intermolecular force in a nonpolar molecule, and they're the weakest of all intermolecular interactions. We're going to look at H2. So this is a perfectly symmetrical hydrogen molecule. The electronegativity value for each of the hydrogen atoms would be 2.2. It's a nonpolar bond, and as a result, it's a nonpolar molecule. So essentially, when we look at, if we were to draw a whole bunch of H2 molecules, there's no reason for one H2 molecule to be attracted to another. There's no positive negative type interaction, and as a result, that means that the molecules are held together very weakly. Okay, this we recognize if we were to actually examine the boiling point. Now, you do not need to know the numerical value for this, but the boiling point of hydrogen gas, or sorry, I should say elemental hydrogen, is minus 260 degrees Celsius. Okay, that's extremely cold. That's the point at which all intermolecular interaction is broken. The next strongest type of intermolecular force is known as Dipole-Dipole forces. These are the dominant force in polar molecules. So once you can establish a molecule as being polar, you know that immediately it has a stronger intermolecular interaction. Alright, so if I examine HCl, the electronegativity difference between the two atoms is about 1. Okay, it's a very much a polar bond. Alright, and as a result, it's a polar molecule. Okay, I can put the delta positive, delta negative partial charges in this, but what I'm really going to do is I'm going to look at what happens when a bunch of HCl molecules get together. Well, the positive end of one molecule is attracted to the negative end of the other, and so on and so forth. As a result, HCl molecules are held together much more strongly than H2 molecules were. Okay. This, again, I could look at in terms of what is the boiling point. Hydrogen chloride boils at minus 85 degrees, which is still exceptionally cold, but it's much, much warmer, almost 200 degrees warmer than H2 boiled at. Right? This is a result of the much stronger intermolecular interaction between adjacent HCl molecules. So we see this again boils at minus 85, much, much hotter than H2. Okay, the third type of intermolecular force that we'll look at is a special case of dipole-dipole interactions. It's known as hydrogen bonding. Once you draw the Lewis structure for a molecule and you realize that there's a hydrogen bonded to either nitrogen, oxygen, or fluorine, NOF, the dominant intermolecular force is going to be called hydrogen bonding. Now, this is a result of the very large electronegativity difference between hydrogen and each of nitrogen, oxygen, and or fluorine. Okay, so if we draw a water molecule, we can see that water has very much a delta positive and delta negative end. And when we get a whole bunch of water molecules together, what happens is each of the oxygens is able to sort of interact with two hydrogens, while each hydrogen can interact with another oxygen. As a result, you get this very extensive network of intermolecular interactions. As a result, again, the boiling point of water is almost 200 degrees warmer than that of HCl. So it's much, much hotter than a dipole-dipole intermolecular force type molecule. Alright, so what we can take away from all of this is that a molecule that has London dispersion forces, has a lower boiling point than that which has dipole, which has a lower boiling point than that has hydrogen bonding. The other two types of intermolecular type interaction we can look at are ionic and metallic interactions. So ionic compounds have many interactions between positive and negatively charged ions. Each one is small in and of itself, but the sum of millions and millions and millions of them results in much higher melting and boiling points than any type of molecular covalent interaction. Metals have their own special case of intermolecular, or I guess we'll call it interatomic bonding. It's known as the sea of electrons model, which basically is the result of the large diffuse d orbitals. As a result of this, metals exhibit a much higher melting and boiling points than even ionic compounds do. So again, in summary, the weaker the intermolecular force, the lower the melting and boiling points. The stronger the intermolecular force, the higher the melting and boiling points. You need to be able to draw a Lewis structure, determine polarity. From polarity, you can determine the intermolecular force. Once you can establish the intermolecular force present, you can establish which of a list of compounds has the lowest boiling point, which has the highest.